So good evening, all of you. Here we are doing a very important topic, and this is about circles. So as you know, in circles there are various theorems. These theorems are very important. You should understand the theorems. Only then you can solve the questions based on circles. So the important theorems that we have here is the first one is about an arc and the angle subtended by an arc at the center and on the remaining part of the circle. So I'll take this arc. Suppose this is an arc AB. Okay. So this let us now how to represent a circle. Now circle can be normally represented like this: C circle, O center, and R radius. Okay. So this is the normal representation of circle COR. So that means it's a circle with center O and radius R, right? Now once you have this one, circle with center O and radius R, now suppose we are looking at this arc AB. Now arc AB is represented by this sign over the top, right? Arc AB. Now you have to understand that this arc subtends. Subtends means to form. The word here is subtends. Subtends means to form or to look at the endpoints, and if you join that point with the point from which you are viewing it, that is called subtend. Normally there is a difference, there is a slight difference between subtend and form. In subtend you are having what? The endpoints are being looked at from the point. That is what is the meaning of subtend here. So normally in the case of circle and your sphere, you would use this. Even trigonometry, this word is used. This is known as subtending the angle, right? So this is a very important one. So this the word here is subtends. So this is a circle with center O and radius R. This arc is arc AB. It subtends an angle AOB at the center and angle APB. So I'm writing this like this. This angle APB is on the remaining part of the circle. So now a circle is divided into two parts by this arc AB. One is this arc AB and the remaining part is this one APB, right? So if arc AB is minor, then arc APB is major. So if we cannot look at this angle here, that will be wrong because we have to look at the other part of the circle. That is why the theorem goes like this: the angle subtended by the arc AB at the center is double of angle subtended by the same arc on the remaining part of the circle. That is our theorem, right? So now how to prove it? What you have to do is simple. Just join OP. Join OB. So we'll take three cases here. First, arc AB is a minor arc. Then arc AB is a semicircle, and then arc AB is a major arc. So first, let the AB be a minor arc. So for a minor arc, this kind of diagram you can make. Now this is angle 1 and this is angle 2, right? So from the symmetry, what you can see, this OP is equal to OA because they are both equal to radii. So I can write OP is equal to OA, both equal to radii. Similarly, OP is equal to OA, right? Angle 1 is equal to angle 2. Isosceles triangle property. If OP is equal to OA, then angle 1 is equal to angle 2, isosceles triangle property. Similarly, here we can write this angle 3 is equal to angle 4. Similarly, we can write angle 3 is equal to angle 4, right? Now look at this. In triangle POA, this must be an external angle, right? Exterior angle. Exterior angle means the sum of interior opposite angles is equal to exterior angle. So if I write this as, suppose some angle Q, so AOQ, angle AOQ, right, is equal to the angle 1 plus angle 2. But angle 1 and 2 are equal, so we can write this as twice angle 1. Let this be equation number 1. Okay. Similarly, we will look at this angle. Suppose BOQ. Angle BOQ is 3 plus 4, but 3 and 4 are equal. So we'll write this as angle double of angle 3, right? Now what you can do is you can add AOQ and BOQ. So what you will get when you add AOQ and BOQ, right? Angle AOQ plus angle BOQ, that comes out to be twice angle 1 plus twice angle 3. So 2 can be taken as common now. So that comes to be angle 1 plus angle 3 and double of angle 1 plus angle 3 is what? APB. So that gives us angle APB. So that proves for the minor arc this theorem is proved. Similarly, we can do it for the major arc and for the semicircle. So semicircle will have a special theorem or corollary for this. But right now let us look at for major arc. If this arc AB is major, then we can draw this diagram this way. Suppose this is the diagram and then this arc AB. So we have to now look at this major arc. This is the center, right? So the remaining part is the upper part. So let this center, the angle subtended by this arc, major arc will be this one, AOB. And on the remaining part, the angle subtended is angle APB, right? Again, the theorem goes like this. Join this. Now AO is equal to PO, just like before. So we can write angle 1 is equal to angle 2. Similarly, this PO or is equal to BO. So we can write angle 3 is equal to angle 4. So this angle is angle 1 plus 3. And suppose this is Q, AOQ is angle 1 plus 3. And this angle is angle 3 plus 4. So as you can see here, this complete angle reflex angle AOB, reflex angle AOB is equal to angle 1 plus 3 plus 1 plus 2 plus 3 plus 4. Now 1 plus 2 is what? Double of, now 1 and 2 are equal as you can see. So I can write this as twice angle 2 and this as twice angle 3 or twice angle 2 plus 3 or twice angle APB, right? And this is how we can prove it for the major arc. Now comes the semicircle. For semicircle, AB will be a straight line, that is, it will be a diameter. So semicircle, this is a semicircular arc, right? So you can take it any sides, this side also, this side also. So I am taking this side. Now again APB. This is the center, and since this is a semicircle, then AB becomes a diameter. So AB here is a diameter, right? AB is a semicircular arc, therefore this angle here is 180 degree because AB is a straight line, or angle AOB is equal to 180 degree because AB will be the diameter, and you can similarly make the same kind of diagrams here this way, and again you can use the same logic. This way we can write x, so this becomes 2x, this angle is y and this angle is y, so this becomes 2y. So 2x plus 2y, right? 2x plus 2y comes out to be angle AOB. But what is angle AOB? 180 degrees. So we can write x plus y is equal to 90 degree. But look, what is x plus y? Angle APB. So we get angle APB is equal to 90 degree. So that proves our corollary, that is angle in a semicircle is a right angle. Angle in a semicircle is a right angle, right? So that is again a very important theorem, right? Now sum of angles of cyclic quadrilateral. Let us see what is the cyclic quadrilateral and how it is important. In a cyclic quadrilateral, a quadrilateral whose endpoints lie on the circle, right? Not inside the circle, but on the circle. For example, you have this circle, and these are the endpoints. So we have the endpoints A, B, C, and D. If the endpoints lie on a circle, then quadrilateral ABCD is a cyclic quadrilateral. Okay. Quadrilateral ABCD is a cyclic quadrilateral if A, B, C, and D lie on the circle. They should be on the circle and it should be a quadrilateral. Now, and let O be the center. So this is a circle with center O and radius R. COR means circle with center O and radius R. Now we have to prove that opposite angle sum is 180 degree. Sum of opposite angles is 180 degrees. This is what you have to prove. Now there are various method. You can use this theorem that you have just proved earlier. That can be done if I join this. Suppose I look at arc ADC, and don't take that this center of this circle is same as point of intersection of the diagonals. That is not necessary. So one method is this one. If you look at this angle, then this angle ABC will be half of this angle. So suppose if I take this angle as x, then this is going to be 2x. Similarly, if this angle is y, then this angle will be 2y. Look at this arc ABC. It subtends this angle y on the circle, so this angle other center will be double angle. Now, angle at a point, the sum of the angles at the point is always what? Sum of the angles at the point is 360 degrees. Therefore, we can just divide by 2 and you will get 1 plus x is equal to 180 degree, or y plus x is equal to 180 degree, and that completes our theorem, that is angle B plus D is equal to 180 degree, right? So that is one way. And of course, similarly, you can prove that angle A and C also the sum is 180 degree. Now, of course, there is another way, and that is quite interesting. If you look at, say, for example, if you just join BD and AC. Now, before that, we should know that angle in the same segment are equal. So we'll prove that theorem also. Angle in the same segment. Angle in the same segment. Now, what does this word segment here? Segment is normally this part of the circle. So here we can just look at the arc part. Segment means this chord divides this circle into two parts, the upper part and the lower part. So here also we can use this theorem. Angle in the same segment means, suppose we have one arc AB, it makes one angle here on the circle, this angle, another angle here, this angle, then angle 1 and angle 2 are equal. This can easily be proved if you just look at the center. Suppose O is the center. So this angle is 1, then this is double of 1. This is 2, then this is double of 2. But double of 2 and double of 1 are the same angle AOB. Therefore, 1 must be equal to 2. Because the double is same, therefore they must be the same angle. So this is how angle in the same segment is proved. That can be used here. Suppose I take this angle as this angle ABD as x, then angle ACD is also x, as you can see, right? Now, if this is x and this is x, let me take one more angle here, okay, so that we get angle sum property here. Look at this angle now. Yeah, if this angle is y, now from this segment AB, this angle BCA is also y, right? So angle BCD becomes x plus y. So what is angle BCD plus angle BDAB? Angle DAB. Now this sum is 180 degrees. Now BCD is what? Nothing but x plus y, and DAB. Where is DAB? DAB. DAB is our angle A. Now this we have to prove 180 degrees. So I'll just write this much like this. Now look at this angle. Now DAB, x and y are also angle of a triangle, and we know that angles of a triangle by angle sum property is 180 degree. So we have just proved that angle BCD plus DAB, angle BCD, this one, that is angle C and angle A, their sum is 180 degrees. So this is another way of proving angle, that is ABCD is a cyclic quadrilateral, and the opposite angles of the cyclic quadrilaterals are supplementary, right? Now, we have very important theorem coming up, that is alternate segment theorem. Now, alternate segment theorem, in this theorem, you have to look at one chord, one tangent, and the angle subtended by the chord on the circle and formed by the tangent. So what I mean here is, suppose I have a circle here, and this is a tangent at point, say point of contact is P, and suppose we have this chord AP, right? So I'll write this is a tangent here, LM. AP is a chord. It subtends, it makes an angle here APM with the tangent, and on the remaining part of the circle, it makes this angle. Suppose this is PBA, right? So you have to prove that this angle PBA and angle APM are equal. This is a very, very important theorem. It is used a lot of times. Okay. So how it is proved? Suppose this is the center O. Now we can join center with OP and OA, right? So now you know that if this angle is, start with here. Suppose this angle is X. Therefore, this angle is 2x for sure, right? This angle is 2x, and suppose we got this angle as y here, right? And we also know that the angle between the that is radius and the tangent must be what? The angle between the radius and the tangent is 90 degree, right? So this angle here is 90 minus y. Yes or no? So this angle is 90 minus y here, and this angle is y. And we can do it, prove it other methods also, but this is a quite interesting one. So this is x, this is 2x, this is y, this is 90 minus y, right? If this is y, then this is also y, right? So this is y, this is y, this is 2x. So y plus 2x is equal to 180 degrees, okay? And that gives us 2y plus 2x is equal to 180 degree. That gives us y plus x is equal to 90 degree, right? So we can get x here as 90 minus y. So this x is equal to 90 minus y. But if x is 90 minus y, we have already proved that APM is also 90 minus y. So that gives us a simple this thing, that is a angle ABP is equal to 90 minus y, and angle APM is also 90 minus y, and hence our alternate segment theorem is proved like this: angle ABP is equal to AP B. That's it. A angle ABP is equal to APM, right? So I should write here ABP, and here I should write APM. So that proves our theorem. That is, now there are the use of alternate segment theorem is a lot. So when you are constructing tangent to a circle, then this theorem is used a lot, right? And of course, we'll do one standard question based on this if you want. That can be solved. It's actually in the tangent related theorem, but it's a very important one, right? When you are doing tangents to a circle, this is a very important theorem, right? And one more theorem that is we can look at here is only one and one circle passes through three non-collinear points. So suppose we have got what? A, B, and C. So now we have to prove that only one circle can pass through these non-collinear points. To do that, what we are doing, we are just forming a triangle maybe, okay? And now what I do here is I draw the perpendicular bisector of any two sides. Say for example AB and BC, the perpendicular bisector, if you draw this one and this one, okay, let them intersect at point O. Now we know that in a plane two lines can intersect at most at only one point, so O is unique. O is unique because it's the intersection for two lines, right? So point of intersection is unique for the perpendicular bisectors. Point of intersection is unique for the perpendicular bisector. That is our first point. Now join OB, OC and OA. You can easily prove that since this is a perpendicular bisector, this angle is 90, and this whatever, suppose M, or say whatever, we can write Z. BZ is equal to CZ, right? BZ is equal to CZ, and OZ is common. This is 90 degree. So angle 1 is equal to angle 2 here. So angle 1 is equal to angle 2, 90 degree, and these two sides are equal. So therefore we can say that triangle BOC is congruent to triangle BOZ, that BOZ is congruent to COZ, right? Now that means if these two triangles are congruent, that means BO is equal to CO. Similarly, we can prove that this triangle, suppose this is Y. Okay, let's write X, right? B triangle BXO, triangle BXO is congruent to triangle AXO, as you can see here, right? Similarly, if these two are triangles congruent, so we can write AO is equal to BO. But BO is already equal to CO, so we can write AO BO is equal to CO. Now, since AO is equal to BO is equal to CO, we can take this as some radius R, and taking O as center, we can draw a circle which will definitely pass through A, B, and C. Therefore, we will get a circle. But why is the circle unique? Because the center here is unique. Why? Because the two lines here can at most intersect at one point. Therefore, O is unique, and if O is unique, then this circle is unique. Therefore, we have just proved that one and only one circle passes through three non-collinear points. So these were some of the very interesting theorems of circles. So those who are studying maths and should be able to understand these theorems and how they are proved. They are logical, and they are of course they are having a lot of use here in solving very simple kind of questions in circles also. So you should be aware about these theorems, and there are many more, but these are some of the basic ones. And solve some of the questions, and if you have any queries, you can just write in the comment box about the questions, and probably I'll come up with a video to give you answers for that. Okay, so keep solving questions, and hope you enjoy this session. Right, thank you for watching, and see you in the next one.